Good afternoon, everyone. I'm Jiayi, a first-year PhD student at the University of Chicago and the first author of this paper. And this work was largely done during my time as an undergrad at the Chinese University of Hong Kong, Shenzhen. Together with my amazing co-authors at the University of Chicago, Microsoft, and Stanford, I'm excited to share our work, CacheBlend Fast Large Language Model Serving for RAG with Cache Knowledge Fusion. So before we dive in, let's quickly review how IM inference works in two phases. Suppose the user asks, how many goals the message score at the FIFA World Cups? Retrieval augmented generation setting, RAG. Relevant documents are first retrieved from the external sources, the user query, and together with the retrieved documents are fed into the LLM, which underwent the preview phase, which generates the KV cache and also the first token. In the decoding iteration one, the KV cache is and the first token generated are together fed into the decoding phase, and then we have the KV cache of the previous token and also the next token. Then in addition, this next token goes is further fed into the decoding iteration 2, and also the KV cache from the preview phase and the decode phase are concatenated together and then fed into the next decode iteration. And then finally, we have the last token generated, which is simply a period in this case. So while the retrieved context in RAG can provide better or more accurate responses for users, it's not free lunch. It comes at the cost of longer prefill delay. For this figure, we are using two A40 GPU to host the Llama 3.1 70B model with a 4-bit quantization. And the y-axis here is the TTFD, which measures the prefill delay in seconds. And the x-axis here is the context length, which corresponds to the total number of tokens in the input. So as shown in this figure, the prefill delay, or in other words, the time to first token continues to increase with longer context length. So opportunity to reduce such delay is prefix caching. And here's how prefix caching works. And this is the same example as our previous example. The query is still how many goals the message score at FIFA World Cups, and the document is still about message scoring information. So let's assume there's another query that queries the same document here. For example, did Messi perform well at the FIFA World Cups? And then we can reuse the KV cache from the previous generation. And in this way, we no longer fed the raw text into the M. Instead, we feed the KV cache of the document one into the M. In this way, we can significantly accelerate the generation because we no longer need to regenerate the KV cache of document one anymore. So, however, prefix caching can be very limited, especially under RAG scenarios. For example, assume there's another query like who scored more goals at FIFA World Cups, Messi or Ronaldo. Probably still we need the document about Messi, but in addition we need the document about Cristiano. Let's assume the AMs have seen these documents before and we have already stored their KV caches. However, in this case, we can still reuse the KV cache of document 1 because it's still a prefix. However, the KV cache of document 2 can no longer be reused because it's no longer a prefix anymore. So yes, even though we have 100% of the KV cache within the system, we can only achieve 50% cache hit rate. So and even more, as the number of documents increases, the hit rate will decrease accordingly. So yeah, people would naturally wonder, since we already have the KV caches within the system, why don't we just put the KV cache naively together? This does not work because it gives bad generation quality. Why is that? Because the cross attention between these two documents are not preserved. So for example, on this left figure, this attention matrix, for example, this 18th row and the 7th column represent the attention word, in some sense, the semantic correlation between the 7th token, which is in document 1, and the 18th token, which is in document 2. And with full KV reuse, we can see the attention matrix, but comparing the lower bottom part, the left bottom parts of these two attention matrices, we can see that for full KV reuse or naive concatenation, the cross attention is completely ignored. So in CacheBlend, we tackle this problem via selective recomputation. That is, we only recompute a very small number of tokens for non-prefix tokens. As shown here, the generation quality is largely improved, while we can still reuse most of the KV cache within the input. So here's a small demo. On the left, it's a standard VM engine. We retrieve 5 chunks, each chunk about 5,000 tokens, and it usually takes, let's see, 5 seconds to generate, which is pretty long. For the VM engine with CacheBlend optimization, still the exact same setting. It's faster, around 1.5 seconds. So the key idea behind CacheBlend is that we are able to maintain the generation quality by recomputing only a very small number of tokens KV cache. In addition, that small amount of overhead can be pipelined with the loading delay. So in this way, we can achieve both high generation quality and very low recompute overhead at the same time. So yeah, now I'm gonna go through our system overview. For existing rack system, it's pretty simple and straightforward. We have a user query, then we have a bunch of retrieved documents, and then together with the user query, they're fed into the M engine, then it gives the correct output. For our system, we start with the same user query and also the retrieval process. Then we have a KV cache loading control that stores and retrieves the KV cache from external storage. And the benefit of such storage extension is huge, because for every copy of the KV cache we save, we can always achieve 100% cache hit rate, as long as it's going to be reused sometime in the future. And also, the retrieved KV caches are then sent to the KV cache blender, which does selective recomputation to fuse the KV cache together. And that KV cache is further injected to the AM engine, and the output is generated. So the two key innovations in our system are the KV cache blender and the KV cache loading controller. And we start with the most important component, which is the KV cache blender. So for the first part of the KV cache blender is about how to recover position encoding. So in normal preview, we have position encoding for a KV cache, meaning that the same KV cache are position encoded with different values at different positions. Then for normal prefix hashing, the same KV cache is always stored at the fixed position. However, this does not work for arbitrary KV caching or non-prefix KV caching, because the KV cache can be reused at any given positions. So instead, we cache the KV cache before position encoding, then we can recover it on the fly when we actually see where the KV cache is going to be reused. And now, because the more important part of the KV cache blender is selective recomputation. So we start with normal preview, or known as the full KV recompute. Let's say we have 8 tokens in the input. On layer I, we have an input embedding which corresponds to 8 tokens, 8 rows in this matrix. And then we have linear projections for Q KV matrices. And this Q and K are multiplied together. That generates the attention matrix. This further multiply with the V matrix. Then we have the input embedding for the next layer. And this gives us the complexity in an order of the total number of tokens. So what if we recompute only 2 tokens out of these 8 tokens in the input? So we have a smaller input embedding, which corresponds to 2 rows, and the QKV vectors are also smaller. Note that we have already pre-computed the KV caches of all the input tokens. Then we can try to update these KV caches correspondingly. And then similarly, this QK yields a attention matrix, and further we have the input embedding for the next layer. So yeah, so in this way, we can reduce the compute overhead from the complexity from the total number of tokens in the input to the number of selected tokens. So now the question becomes how to select tokens, or how do we know which tokens should be recomputed? So yeah, by looking at this figure, this x-axis is the KV deviation, and this y-axis is the cumulative distribution function. So the definition of a KV deviation is very straightforward, which measures the L2 norm difference between the pre-computed KV cache and the fully recomputed KV cache. And by looking at this cutoff line, we can see that the fraction of high KV deviation tokens is very small. So we would naturally wonder, can we just recompute these high KV deviation tokens? Luckily, that works. In this figure, we show the effectiveness of such recomputation. The y-axis is the forward attention deviation, which will be later explained, and the x-axis is the ratio of recomputation, in which we always recompute the high KV deviation tokens. So the definition of forward attention is the attention between the context documents and the query. And the definition of forward attention deviation is the forward attention as the L2 norm difference between the forward attention conditioned on the pre-computed KV cache and the forward attention conditioned on the fully recomputed KV cache. And Q is simply the user query. So this measurement can somehow tell us the output deviation or the effect of the missed cross attention. So by looking at this line, we can know that by recomputing only a very small fraction of high deviation tokens, we can already greatly reduce the forward attention deviation. And for the however, this is not enough, because we do not know how to compute the KV deviation, because in order to do that, we need to know the fully recomputed KV cache, which requires full recomputation. So this requires our third insight. But looking at this figure, the y-axis is the Spearman's rank correlation of KV deviation, and this x-axis is the layer pairs. So for example, this first column here means the rank similarity between the KV deviation on the 5th layer and the KV deviation on the 6th layer. So here's the definition of Spearman's rank correlation, a little bit complicated, but I'm going to work you guys through with a simple example. For example, the rank of KV deviation at layer L is 1, 2, 3, 4, 5, which means that the first KV deviation for the first token is highest on layer L, and the 5th or the last token's KV deviation is the lowest. Similarly, for the rank of KV deviation at layer L plus 1, we have 2, 1, 3, 5, 4. Any of the formula equals to 5 in this case because we have 5 tokens in total, and D is simply the difference between these two ranks. So we can tell that by this red line, these high KV deviation tokens are very similar across layer, which effectively means that we can use the KV deviation at early layers to predict as a prediction for the KV deviation for the future for the later layers. So in this way, we no longer need to perform the full recomputation. So here's the overview of our KV CacheBlend. So for example, if we perform full recomputation on the first layer, then starting at the layer 2, we can get the KV deviation between the pre-computed KV cache and the fully recomputed KV cache. Then we can select, in this case, 3 tokens to recompute for the next layer. Optionally, you can further reduce the total number of tokens to be recomputed to 2 on layer 3. And effectively, we're repeating the same process for each layer. And the second component in CacheBlend is the loading controller, which simply does the compute and loading pipeline. So there are some compute jobs on GPU. Each blue boxes here denotes a single layer's compute. We can asynchronously start to load the KV cache from disk to CPU memory, and then similarly from CPU memory to GPU memory. So in this way, the recompute overhead and loading latency can hide each other. Here's the evaluation. We have a very straightforward setup. The data set is a standard rack data set, which is called 2-wiki MQA. And we also retrieve the top 6 chunks with 512 tokens each. And we evaluate on a lot of queries, 1,500. And we use 2 A40 GPUs to serve the Llama 7DB model. And the KV cache is initially stored on disk. So looking at this figure, the x-axis is the TTFD, which measures the prefill delay in seconds. And the y-axis is the F1 score, which measures the generation quality. So for full KV compute or full prefill, it's very slow, up to 3 seconds. For full KV reuse, it's very fast, but it does not have good generation quality. And for prefix hashing, it's slightly faster, and it's expected because it can only reuse the prefix. For CacheBlend with selective computation, it's able to achieve 3x delivery reduction compared with prefix caching, because we can always achieve the 100% cache hit rate, because CacheBlend allows the KV cache reuse beyond prefixes. And so yeah, and similarly, we have the same setup for throughput evaluation, and that 3x delay reduction can be equivalently translated to this 3x higher throughput. So yeah, now CacheBlend is already a part of the Amcache project. So this is CacheBlend, and this is Amcache, which is the KV cache layer in the LM serving ecosystem. And then we, of course, have these serving engines like VM and SGLang, and we already have the upstream support from VM, and also we are working on SGLang as well. And then together with these serving engines, Amcache has already been adopted by a lot of users such as Bloomberg, LinkedIn, and FlowGPT. Of course, the KV cache layer or Amcache can also help the ecosystem to abstract away the complexity of these storage and compute layers, such as PlyOps, Weka, and Redis. Yes, I think this is the end of my presentation.